Okay, let's get started. So today we're going to talk about a new topic. Right? We have finished the introduction of SVM kernel methods. Right? Now we're going to proceed to artificial neural nets. Right? Perhaps this is the most focus in the cutting edge research industrial applications right now, like artificial neural nets. And indeed, the neural nets resurgence has been lasted for, I think, 10 years. Now it has already, this type of approaches, neural networks and all kinds of architectures and computational hardware, including GPUs, TPUs, have already transformed our world, right? Including I guess most recently, this so-called like large language models like ChatGPT has made people feel like, okay, maybe artificial intelligence really becomes artificial intelligence, right? Yeah, but the implementation of large language models are based on neural network as well. Right? So that's why we're gonna spend quite a few lectures, talk about the foundation of neural networks. So the learning algorithm we have reviewed so far include decision trees, ADA boost, bagging, least mean square, perceptron, and so on. Right? And through the discussion of this learning algorithm, we also talk about several principles for learning, right? So we talk about what's the definition of overfitting. That's when we discussed about the decision trees, right? We found that decision trees are really, really expressive. But when the data contains noises, decision trees will tend to fit the noises as well. And such noises usually will mislead the learning of decision trees and hurt the generalization performance, so-called overfitting, because you're not only fitting the useful supervised signal in data, you also try to fit the harmful noise information or incorrect information. That's why we call it overfitting. Overfitting is not favored in learning, which we always want to try to avoid overfitting or reduce overfitting. Then we'll talk about a little bit computational learning theory. Our goal is not to introduce the details about those theories. We just want to give you some more rigorous framework that can characterize what is the generalization behavior of a learning algorithm, right? So what is appropriate definition of a good learning algorithm? That is so-called PAC learnability, right? Probably approximate correctness, right? Because the training data is random. You cannot expect that every training is gonna give you excellent result, right? Because it really depends on the quality of the training data. That's why when we talk about the generalization performance, you should use some probabilistic statement, right? With high probability, your learning algorithm will find a hypothesis whose true error or generalization error is small, right? That's the right way to discuss or define the performance of a type of learning algorithms, right? And then we talk about hypothesis choice and the VC dimensions, and we use tail bounds to derive the sample complexity bound and the generalization error bound, right? So from the structure of the generalization error bound, we found that, okay, the generalization error bound or true error, right, is upper bounded by your training error plus some term determined by VC dimension, right? VC dimension of a hypothesis It just means, okay, to get a good generalization error, only have a very super small training error is not sufficient, right? Because the bound is also determined by another term, which is which is related to VC dimension, right? So it basically means that if you want to get an algorithm which generalize well, right, you not only need a small training error, that means you fit the training data well, you also need to control the complexity about your hypothesis, model space, right? You won't want your model to be super complex, which leads to large VC dimension, right? So you want to find the best trade-off between the two, right? That motivates the so-called regularized empirical risk minimization, right? So empirical risk minimization means that, okay, during your training, you just minimize some loss function over the training data. You want to minimize the training loss as small as possible, right? And regularized empirical risk minimization tells us that's not sufficient, right? You must also need to consider the complexity of model. That's why in your learning objective, you should include some regularization term. Like in SVM, we put this quadratic norm of the weak vector, which essentially tries to encourage large margins. Okay. So yeah, before we proceed to neural networks, we just want to step back and look at what we have discussed so far. We want to organize our knowledge in a systematic view, right? Because we have we have had discussed quite a few learning algorithms and also look at several important concepts, right? We don't want to get lost in those methods, right? We should have a thread to connect all those topics together. Okay. And so far, we spend most of our energy and time in discussing linear models. Right? So, least mean square are about linear regression, perceptron and the support vectors are about linear classifiers. So, linear classifiers obviously is a good starting point, a good topic because the model itself is simple enough, but it also gives you a lot of insight about how to train a model, how to define a hypothesis, and so on. Right? But obviously, to be practically useful, linear classifiers are not sufficient because in practice, you won't assume that, okay, the relationship between your prediction of interest and your features are always linearly correlated. It's not like that, right? And the real world contains many complex nonlinear relationship, right? And how do we automatically leverage that, automatically extract such kind of relationship from data to facilitate or improve our prediction performance? So people naturally want to build up a more powerful nonlinear classifiers or nonlinear regressors. Right? And so far, we have introduced one way of doing nonlinear classification. What's that method? SVM, yeah, SVM. And what is a particular method that we can use to produce a powerful nonlinear classifier? Yeah, kernel method, right? Kernel trick, kernel method. So this might be like a very straightforward extension of linear classifier, right? You preserve all the computational advantages and simpler structure within linear classifiers, right? What you need to do is just to come out some feature mapping, right? As long as this feature mapping itself is nonlinear, right? Even you preserve the linear structure in your model because the feature has already been transformed in a nonlinear way, you'll eventually get a nonlinear classifier. Like your predictor now becomes W transpose phi x plus B, right? So this is still a linear structure, right? But in terms of x, in terms of relationship between y and x, they are highly nonlinear, right? Why? Because the phi fulfills the nonlinear transform of x, right? Even you plug in a linear structure in a higher level, but eventually the relationship between y and x has been highly nonlinear. Right? And then to reduce the computational cost, like you don't want to do some explicit feature mapping to very high dimensional space, then we can use the kernel trick that motivates our dual SVM form and so on, right? So far we have seen one effective trick to generalize linear classifiers to nonlinear classifiers. That is kernel trick and feature mapping, right? That's one idea, right? But we can also think about another idea. Why not we should extend some existing classifier? Why not just build a nonlinear classifier or nonlinear regressor from scratch? Can we do that? The answer obviously is yes. And artificial neural network is one most promising example of this. Okay, so here's our plan, right? We're gonna first introduce what is a neural network, right? And by the way, there are like hundreds or tens of hundreds of architectures in neural networks. I mean, so it's a big fashion to design new architectures of neural networks. We're not gonna do that because it's not a deep learning class, right? We're gonna focus on very preliminary, very simple structure, but very classical structure. It's called feed-forward network. Sometimes it's referred to as multi-level perceptron. So based on that, introduce what is a neural network, right? What is the architecture? What's the definition, right? Then we'll talk about the rule to conduct prediction, which we call forward pass. It's like you have some feature information in the input level, right? You're gonna pass those information into a set of filters layer by layer until in the output layer, you're gonna generate prediction. So that's why we call it forward pass. And then we'll talk about how do we train a neural network, right? And you find that the biggest challenge is how to efficiently calculate the gradient of your loss function with respect to every parameter of the neural network. Right? You find out, okay, if you just calculate gradient, that will be extremely inefficient, right? Given that the modern neural networks might contain, it's not uncommon to have like 1 million neurons and the weights and so on, right? So you don't want to compute those gradients very, very inefficient, right? So then we're gonna introduce the so-called backpropagation, right? Backpropagation. So you will see that the backpropagation essentially is a very, very smart usage of the chain rule when we learn our calculus, right? In calculus 1 and calculus 2, everybody knows chain rule, right? And backpropagation is just a very smart application of the chain rule. In that way, you kind of avoid any redundant computation. You just catch the results from the previous layer and add a little bit more additional computation to get the gradient with respect to the neurons and the weights at the current layer and going back to the previous layer and going back until you reach the input layer. So that will be our focus throughout our discussion, and our homework, I guess, will be last homework. You will be asked to implement backpropagation by yourself. Right? And finally, we're going to introduce some practical concerns of neural networks. So neural networks is not like a magic sword, which can do everything for you. Actually, how to make it work and how to apply it properly really matters. It requires a lot of experience. So like make neural network to work is more like art, not science or engineering, right? So we're going to talk about like some rules of thumb how to effectively leverage neural networks, how do you adjust the architectures and tune them, all kinds of ways. Okay, this is our plan. So first, what is a neural network? Right? As like what we have discussed for other machine learning models, right? We need to first figure out what is the hypothesis space of a neural network, right? And given a particular hypothesis in the neural network hypothesis space, what is the properties of that hypothesis, right? You see that actually a hypothesis of a neural network space is defined by the structure, right? And actually the structure reflects the expressivity of a neural network, right? So let us start with this structure. We've seen this structure before, right? This is just a graphical illustration of a linear classifier, right? In the neural network literature, people call it linear threshold units, right? So let's see what's the definition, right? So suppose you've got several features. So here we have 4 features, x1 to x4, and we add a constant feature 1 here, right? And then we connect all those features or send all those features with constant 1 to an intermediate node, right? So how do we send those information, those features, and aggregate them at this intermediate node? We assign a weight on each edge connecting a feature to this intermediate node, right? That just means, okay, when I send x1 to the intermediate node, I'm gonna amplify x1 by weight w1, right? And similarly, I'm gonna amplify x2 by weight w2, and so on. And finally, I'm gonna amplify this constant by b, right? It's just telling you, this just tells you that, okay, I'm gonna consider this bias term b, right? Then when these all 5 signals are collected by the intermediate nodes, right? And we can see that we have some operation on this node. Sigma just means sum. So it basically means, okay, I'm gonna sum up all the incoming messages. And this will be my result, right? So this is basically the result of this intermediate node, or the output of this intermediate node, just the summation of all the incoming message plus b, right? And then I send my output to the next node. We call it threshold node, right? So this is basically means, okay, I have some thresholding operation over the incoming message. So here thresholding is just the sign function, right? The sign function of the linear combination of those features and the pass parameter. Right? And then this output of this threshold unit is just the classification result, right? Either positive or negative. Right? This is just a graphical representation of a linear classifier. Any question? Okay. So we can see that using these input features and edges to intermediate nodes, I can represent a linear classifier and the rule of doing the prediction, right? And many of our previous discussions are talking about how do we learn the parameters for this linear threshold, right? The parameters actually are the weights on the edges, right? So W1 to W4 and B, right? So we talk about perceptron, we'll talk about SVM, we will talk about dual SVM. And we should come out some objective functions, say a loss over the trained data, we minimize the loss to estimate W1 to W4 and B, right? So now think about from the graph structure, right? I want to make more complicated structure. that support nonlinear classification. So obviously, one single linear threshold unit, one single just means one single block, right? Just represents the linear relationship between your class label and your input features, right? And can we come out a more complex structure that is flexible enough to express nonlinear relationship between your features and your output labels? And one simple and intuitive way is that, okay, we know that in one linear threshold unit block, right, all those inputs are coming from data, right? And what if I make every input to be the output of another linear threshold unit? So X1 is not the real feature one from your data, right? It just comes from the output from another linear threshold unit. And so is X2, X3, X4. So let's look at the structure, right? So suppose this is my original feature vector, right? X1 to X4, right? Now, I'm gonna construct a first linear threshold unit to generate the first output, right? So I'm gonna use this output as the input to the previous linear threshold we just discussed. And similarly, I can construct a second linear threshold unit, which do some kind of transformation from the original feature set to some output, right? And then I send this output as the second input about my linear threshold unit, right? I can keep doing this, right? I can construct 4 such linear threshold units and use their outputs as input to my final linear threshold unit. So now I want to ask, what's the relationship between your final output, namely the prediction, and your original feature set? Is that still a linear relationship? No, right? Because in the intermediate level, right, you actually have some linear combination of those all those features, but you perform some sign function, right? Sign function is nonlinear, right? And then you throw them into the next linear threshold unit, right? So in this way, we actually build up a simple 2-layer feed-forward neural network. So this is how we build up a neural network. Okay? So it's like we have 2 layers, right? First, the input layer is not considered as the layer of the neural network itself. It's just the data, right? And then we have one hidden layer, which collect from the units over the input layer, right? And serve as input to the linear threshold unit in the next level. And once we collect the result for that linear threshold unit, we get the output layer, right? So we can view this hidden layer as some kind of transformation of the original feature set, right? And this transformation can be a nonlinear. Right? And similarly, you can construct even more layers. For example, I can further construct a set of linear threshold unit to form a second hidden layer, right? And then use this second hidden layer output to fit a linear threshold to generate the final output, right? In that way, you got 2 hidden layers. You actually can do it as many layers as you want. This is how we construct typically a neural network, right? So it's like building It's like building a Lego, right? And your basic block could be very simple, just linear structure plus some functions, thresholding function, right? And then you just put them all together and use the output of one building block as the input of next building block, and you can concatenate them as many as possible, as long as you will like, okay, this is enough flexible. Okay, any question regarding yeah, if you take out this thresholding function, then it becomes it is still a linear classifier, right? It doesn't have any nonlinear nonlinearity here. Okay, that's why later we'll talk about, okay, this thresholding function is in general is called activation function. Okay, and people in practice rarely use the thresholding as activation function. They use like tanh or sigmoid or ReLU. People call them ReLU, right? As the activation function. Right? But we'll talk about that in a minute, right? But anyway, any question regarding how this intuition, how we build up artificial neural network? It's a so yeah, we can see that actually the modern neural network is even seemingly very, very complicated, right? So they're always like built in this way. You have a very simple and basic structures, and you're gonna use all kinds of ways to put them together, connect them. Okay, so in practice, I mean, to be convenient, right? So we don't want to separate this summation and the thresholding operation together, right? We just use one node to represent these two operations. So basically, we use one node to represent the operation that I'm gonna doing the summation over the incoming messages and doing some threshold on that. So this node operation is called a neuron. So you can view that, okay, I'm gonna view these two operations all together by one neuron, two neurons, three neurons, four neurons, and five neurons. So you have in our exemplar neural network actually have 5 neurons. Okay, so now let's try to formalize this. What is neural network? Neural network is a robust approach for approximating real valued, discrete valued, or vector valued functions. From a mathematical perspective, it's better to view it as a way to construct convex function approximations. And later we'll talk about the analogy to the real neural networks, but I mean, from the series of biologists view, like artificial neural nets have nothing common with real neural networks. And neural network is among the most effective general purpose supervised learning models methods currently known. Especially neural networks are good at approximating or learning complex and hard to interpret data, such as real world sensor data, such as brain image data and tumor data kind of stuff. And the training with neural network is mainly implemented through backpropagation algorithms. So there are like numerous successful applications with neural networks, which I do not want to emphasize again. Okay. So how does a neural network compare to a biological neural network, right? So there are only, I guess there are only two terms which you can view like kind of similarity. It's kind of similar, right? Because in biological neurons, the basic, you got like two components for a neuron, right? Dendrites and axon, right? So dendrites is like, you see, it's like a tree branches, right? They're gonna collect the information from other neurons, right? And right now the modern research is just trying to view this as electrical signal, right? And then a pulse signal, those kind of stuff. And the axon is like a processor to generate outgoing spikes, right? Something like this. So you see, if you are interested in neurobiologist research, right, you see that they're always trying to decode or encode such neural signals, a sequence of spikes. Okay. This is like similar to the neurons used in artificial neural networks that collect information from neurons from the previous layer, and then you do some operation, right? It's like axon to aggregate them together, perform some transformations, send them out, right? But this is the only similarity. It's very, very rough similarity. I mean, to be more precise, we could say like modern artificial neurons are inspired by biological neurons, right? But there are many, many fundamental differences. Right? So don't take the similarity seriously, right? And serious neurobiologists will never admit that artificial neural nets are kind of like similar or simulator or approximation to the true neural networks. So this is more like some kind of like words to stimulate your interest on that. I use some fancy words to represent, but it's totally different from the neurons in animals or in human beings. Like, okay, how do we view like artificial neurons? We just view them as something as a mathematical object, right? That very loosely mimic a biological neuron. For an artificial neuron, it accepts a collection of inputs, which usually is represented by a vector x. Right? Remember, this x could be the feature vector, or could be output of our neurons. Right? Then it will produce a scalar output. How can it produce? Right? It will first apply the dot product with some weight vector with x, and then add bias parameter. So it's basically doing this, right? And following it will apply a transformation called activation over this linear transform. Then you'll get the output of the neuron. And this activation is often chosen as a nonlinear function. Later we'll list examples of activations. So now if we take a look at our linear threshold unit, right? So that we can see that this one is actually a neuron, right? To get an output of this neuron, we first apply a dot product with weights W and add bias parameter B, right? Then we'll apply a threshold function over this linear transformation, right? To get the output, right? And obviously other activations are possible. So here are a list. Here is a list of common use activation functions. And of course, if you don't do anything, you will go back to the linear classifiers. This is called a linear unit. Right? The thresholding is how we're going to do classification, right? A sigmoid. This is often common. It's a very common used approach. And rectified linear unit, people call it ReLU. Right? You take the maximum between 0 and this W transpose X plus B. Okay. And tanh. And ReLU was proposed much later than sigmoid and tanh. It was like proposed, I think, about 10 years ago. That was when the neural network researched again. Because previously, like the machine learning our artificial intelligence community are still like dominated by spot-back machines, kernel methods, this kind of stuff, right? Until 2012, a paper published in NeuralNIPS workshop is called, from Jeffrey Hindden's group, it's called AlexNet. Right? So they show that using their artificial neural net with their proposed ReLU activation function, they can dramatically improve the performance on the image classification task, like improve like by 40% accuracy, something like that. And then people started to realize the power of neural networks, especially with super huge data set, right? And then there was a boom of all kinds of neural network architectures and their attempts to make the neural networks to work better and better until now, in terms of like image classification and many other recognition tasks. Using neural network has become the state of art, and in many tasks can even defeat human beings. There are many more activation functions available, such as sine, Gaussian polynomial, and so on. Right? But right now, like, believe the most common use are ReLU or 10H or some variants of ReLU, like continuous relaxation of ReLU. Okay, so once you have constructed a neuron, right? We know that it's the basic unit of a neural network, right? How can we build up neural network? Right? We can view neural network as a function that converts inputs to outputs defined by a directed acyclic graph. Okay. And in this directed acyclic graph, the nodes, also called neurons, are organized in layers, and the edges carry output of one neuron to another. That edges are in charge of sending messages between neurons, associated with weights on those edges, because usually we assume that, okay, when you send information, you're not just send the original information, you're going to amplify it with some weight. Here's one example. Right? So you've got a set of input features, right? And then those input features are jointly sent to neurons in the next layer, right? So we got 3 neurons in the hidden layer, right? Each neuron computes its output by collecting the information from the previous layer. And of course, associated with each edge are a set of weights, right? And you're gonna amplify each incoming message by the weight on the edge and then add them together and perform activation function, right? And once you have collected the outputs of each neuron in the hidden layer, those outputs will be sent to the neurons in the next layer. In this case, like we might have like 2 output neurons, right? Because each of this output neuron will collect results from the previous layer, namely the hidden layer, and then do some aggregation and make the final prediction. And in practice, how do we define neural network? We need to specify the structure of this directed acyclic graph, right? You need to determine, okay, how many layers do you want to use, right? How many neurons will be placed in each layer, right? How each neuron is connected to the neurons in the previous layer, right? And how do you pick up or how do you choose the activation function, right? And in principle, you can make the activation function vary for every neuron, right? But in practice, people will usually choose just one activation function throughout the whole neural network. So once we have identified the structure of the graph of the neural network, we call it, we have designed the model of the neural network. And then the learning of the weights on the edges is from the data. So when we say, okay, we want to train a neural network, essentially we want to estimate those edge weights out of from data. That's the basic that's the basic strategy. Right? So to define or to design a neural network model just means how do you design this structure of directed acyclic graph? How do you pick up the number of neurons per layer, how many layers, and also how to pick up the activation function. Right? And once the structure is there, your network has already been designed, right? Then the learning is to estimate the weights associated with the edges on your neural network. Okay, any questions so far regarding the definition of neural network? Okay. So here is just a brief history of neural networks. It can be traced back to 40s in the last century, right? And then in 1949, Hebb suggested a learning rule that has some physiological plausibility. So yeah, we can see that the neural networks researcher can be traced back to the research on the psychology, right? And then this is Rosenblatt, the perception algorithm, right? And the neural network was motivated by the perception. And later people find that, okay, there could be some problem on the simple perception. And then people found a way to, construct or make more complex structure by just, stacking linear threshold units. You can overcome the limitation of the simple perception algorithm, right? And after that, people have found many other important structure of neural network. For example, the convolution neural network. And people have also invented the important efficient learning algorithm for neural networks. It's called backpropagation. From 2003 to today, we found all kinds of neural network structures and applied to all kinds of data like transformers, right? Spectral convolution and like ResNet, all kinds of stuff. But all of those evolution, right? We can find a lead, a thread to see how those evolution goes, right? That's why we only focus on fundamental structure of the neural network, and based upon that, you can easily extend it or extrapolate to all kinds of other structures, right? Including that, like ResNet. You see that they actually add skip layers between the blocks, between the layers, right? There are some strong reason of doing this, right? But it's not focus of our class today. We just give you some sense. Okay, so next we're gonna discuss the expressivity of neural networks, right? So we said that it's better to view neural network as a function approximation, right? Then the question is, what kind of functions can neural networks approximate, right? So we know that a single neuron, namely the linear threshold unit, right, can only perform linear classifier. That means it can only approximate linear functions. However, if we use linear threshold units to build up neural nets, right? Like you got 2-layer neural networks, and where each building block is just a linear threshold unit. You'll find that it can represent general any convex polygons. Right? It's not only limited to a separating hyperplane. Right? It can represent general convex polygons. Right? Has already been much better. Right? If you construct 3 layers with linear threshold units, in general, it can represent union of any number of convex polygons. Right? So it's even more expressive. So you can see that actually the expressivity of the neural network seems associated with the number of layers, right? So in general, we can conclude that the neural networks are universal approximators of functions. Okay? So there are a set of very famous theory tells us that any continuous function can be approximated to arbitrary accuracy using a neural network only with one hidden layer, only with sigmoid units, meaning that with sigmoid activation function. Okay? So you can see that even you just have one hidden layer, as long as you have enough number of neurons in a hidden layer, you can approximate any continuous function. Okay? Later, people find that this approximation error is insensitive to the choice of activation. So you can use other activations like 10H. Because you still get the same conclusion. Right? In our example, a two-layer thresholding neural network can express any Boolean function. Just as we discussed before, right? For a decision tree, it can represent any Boolean function, right? And we said that, okay, for linear classifiers, of course, you cannot represent. It's not all kinds of linear Boolean function can be represented. For example, XOR function, right? When your function X space parity, right? It cannot be represented by linear classifiers. Right? However, if you just build up concat those linear classifiers to form a two-layer neural network, then it immediately becomes expressive enough to represent any Boolean function, including XOR, including parity cases. So how can we quantify the expressivity of neural networks? Right? As we know that the VC dimension is a good measurement, right? So here are some results. For thresholding neural network, namely the neural network built based upon linear threshold units, right? The VC dimension is determined by the number of edges. So VC dimension is proportional to the number of edges times logarithm number of edges. So you can see that the more edges you have in your neural network, the more expressive, or in other words, the more complex your neural network hypothesis is. If you don't use thresholding as your activation, you use sigmoid, right? Actually, you don't have like some exact form of VC dimension, but you have some bound. Right? So the upper bound of the VC dimension of a sigmoid neural network is the square of the number of nodes times the square of number of edges. And the lower bound is square number of the edges. Right? So you can see that actually the size of neural network reflects the expressivity or the flexibility. No, there's only some bounding estimate. It's very hard. This just want to give us some intuition or some sense like how the expressivity of neural network is associated with its structure. But here, everyone try to do this, right? Try to solve this problem. Show that if you only have linear units, then even no matter how many layers you put in your neural network, it won't change the expressivity at all. Right? Actually, the intuition is that if you just use linear unit, it is still equivalent to a linear classifier. There's nothing changed, right? But it's better for us to sit down and work out this problem. Okay, so any questions so far about the general definition of neural network and how expressive it is? Okay, great. So next we're going to talk about given neural network, how do we perform prediction, right? Which we call forward pass. So we're gonna use this example, okay? A concrete example. We have this two-layer neural network. You got the input feature x1, x2. So x0 here is just some constant feature 1. And similarly, z0 is constant feature 1 to allow some bias term to be integrated into the neurons. Right? So we have a input vector x, hidden layer, z, output y. So here, for convenience, like we use vector to represent the output of neurons of each layer. So this is x, right? This is z, and we got a scalar output y. And the x0 and z0 is bias feature and is always 1, right? And here we assume that we use sigmoid activation. So sigmoid, let me write down, right? Sigmoid just means sigmoid, maybe h is just 1 minus 1 over 1 plus e to the minus of h. This is called sigmoid function. We use sigmoid activation function, right? And here's the important notation, right? So you want to look at how each adjuvate will affect the prediction and the training of the neural network, right? So we need a good way to index those adjuvates, right? So here is our naming convention, right? In the superscript, we use target layer, namely which layer the edge will point to. And in the subscript, we use 2 indices. The index of the source node or source neuron and the index of the target node, right? If we can take a look here, right? So look at this edge. So the target layer is the hidden layer. That's why our superscript is h, right? And in the subscript, we have the index of the source neuron and index of the target neuron. And both indices are 2, right? And similarly, we can take a look here, right? So again, the target layer is hidden layer, so it's h, right? And the subscript, the source node index is 0, and target node or target neuron index is 1. That's why this I represent as WH01, right? And similarly here, right? The target node. The target node or target layer is output layers. That's why you see the superscript O, right? And the source node is Z2, right? The index is 2. And target node or target neuron is 1. So here we just index the output neuron as 1, as 2, 1, like WO21. So now, suppose we're given an input x, or input vector x, that means we have here, right? How do we compute the output of the neural network? Right? That is the output of the neuron in the last layer. It's very straightforward. You just do it layer by layer, from bottom to up, right? So we're gonna first compute the output of each neuron in the hidden layer, because it is just the next layer, one level above the input layer, right? So the first neuron in the hidden layer is Z1, right? So how do we compute the output of Z1? We just do a linear combination of the incoming neurons, x0, x1, x2, right? And we know that associated with each edge is edge weight, right? So that will be W01H. And remember, x0 is the constant feature 1, right? So W01H times 1, right? Plus this guy, WH11, right? WH11 times x1, right? And this guy is WH21, right? WH21. And you get Z1, right? And next, we're going to compute the output of neuron Z2, right? How can we compute them? Similar, right? But remember, there are another set of edges connecting the 3 input neurons to Z2, right? And correspondingly, the edge weights will be different as well, right? So for Z2, we know the edge connecting X0 to Z2, their weight is WH02, right? And again, it's multiplied with 1 because X0 is simply 1, right? And this one is WH12, right? Here, times X1, and this edge weight is W22H times X2, right? And then you apply the sigma activation function, you got Z2, right? And Z0, we know it is just constant feature 1. So that means we have finished the computation of the neurons in a hidden layer. And next, we're going to use the hidden neurons output to compute the neuron in the output layer, right? There's only one neuron in the output layer, just Y, right? So the computation of Y is just a linear combination of the neurons in the hidden layer. So it will be W0O times Z0, which we know is 1, right? And plus this one, right? The edge weight is W110 times Z1 plus this one, right? The edge is W210 times Z2, right? Then you got Y. You might ask, why didn't I apply sigma activation function in front of it? That's just the tradition. In the neural network literature, at the last layer, we usually just do the linear combination. We do not apply any nonlinear activation. Okay? And if you're upset about that, you can do your secret nonlinear activation. No one is gonna blame you. And here we just I'm just telling you, like, people just follow their tradition doing things like this. Okay, this is how we make a prediction, right? And even you have 10 layers, you have 100 layers, the computation is always like this. Right? From the bottom layer, you calculate each neuron's output in the next layer. Once you finish calculation of outputs of neurons in this layer, you feed them to the next layer, compute all the neurons in the next layer, doing this until you compute output of the last layer. Any questions so far? Okay. Then we finished our discussion about forward pass, right? And this is a very important, although it looks simple, because when we compute the loss function of the neural network, right, you have to compute the prediction of the neural network for every training input, right? And then you need to implement this forward pass. So just make sure like you have no doubt on this calculating procedure. Okay. Now let us proceed to the training part, right, which we call backpropagation. Right? So suppose we have a design a neural network. That means we have a specified a particular network structure. We have designed the layout of neurons, their connectivity, and the activation function, right? And I also have collected a data set of labeled examples, which we can view them as pairs of the input feature vector xi's and labels yi's. And the training of the neural network is to learn the weights of the neural network, right? Remember, the weights are staying on the edges, right? We want to estimate the appropriate weights on those edges. And how can we do that? As we mentioned before, right? Neural network is a function, right? For any fixed architecture, we can write down the neural network form, right? F, X, and determined by W, right? Because it's just the composition of a bunch of simple functions together, right? So we can view the prediction of neural network as a function not only of the input feature vector X, but also a function of the edge weights, right? if you take a look at our previous calculation procedure, right? You can see that y not only depends on the input features x1, x2, right? It also depends on all the involved attributes, right? So obviously y is a function of x and also the w's, right? So yeah. So that's why we should will the prediction y is not only the input feature vector, but also the weights, right? And then we can construct a loss for the prediction of the neural network, right? On the training set, right? For every training input xi, right? I got my prediction from neural network, and this prediction is determined by the parameters w, right? Those weights on the edges, right? And then I'm gonna contrast the difference to the ground truth label yi, right? And come out some loss function, for example, a square loss, right? And then my training would be just minimize the loss over the training set, right? And I can minimize this loss with respect to the edge weights of the neural network. Then we call it training. Okay. Any questions so far? And perhaps in practice, you want to regularize the complexity of neural network, you add some regularizer over W, right? But here, let us just forget about it. Let us just assume, okay, we have some loss function on that, right? So we can see that this learning loss construction or design is kind of similar to the previous linear classifiers, linear regressors we have discussed, right? So we can define some loss function, which measures how well you fit the prediction of your model fits the training data, right? And to penalize overcomplicated hypothesis space, you might add some regularizer based upon the model parameters and so on, right? So it actually uses the same idea for nonlinear models, right? So now, given the example we just discussed, right? This two layer neural network, right? Suppose we have some input x, right? And the true label for this example is y star, right? Now, I'm gonna use a square loss for this particular example. Namely, I first use my neural network to compute my prediction, right? Through this forward pass, right? Then I look at the square difference between my prediction and the ground truth y star, right? And use that as loss. Right? Then my goal is that, okay, I want to minimize this loss with respect to my model parameters, namely all those attributes, right? So how can I do that? I'm gonna take the derivative of my loss with respect to every edge weight, right? See WH, IJ, something like that, right? That's the whole training procedure, right? And we can apply stochastic gradient descent, right? It's the same framework, right? So this is my loss function over the training set, right? And as you mentioned, like when you have a huge number of training examples, it might not be wise to calculate the full gradient, right? Instead, we're gonna just use one or few examples to construct a mini batch, right? And then I do the stochastic gradient. I use that to update my model parameters, right? The same framework applies to neural network, right? So given training set, right, we initialize model parameters W, right? And then I go through the data set for many, many epochs, right? Inside each epoch, we first random shuffle the training set. Then we look through every training example, xi, yi. Then I treat this example as the entire data set, then compute the gradient of the loss, right? This is stochastic gradient. Then we just update our model parameters W, which include all the attributes, right? Using this stochastic gradient, that means I need to specify what is the learning rate or step size gamma t, and subtract the current model parameters by gamma t times the stochastic gradient, right? Then you finish one update, then you look at the next example, you do the same thing until you finish going through the whole data set, right? That you finished one by that you finish one epoch, right? You just go through big epochs until and then you finish the training, right? Then you eventually you return the learned weights of the neural network. Okay. Is there any question regarding the training framework? Right. It's the same, exactly the same as we did before, right? And here we want to point out is the objective function of the neural network is typically nonlinear, non-convex. Okay. You cannot expect that, okay, no matter how I initialize the model parameters, I'm gonna arrive at the same global minimum. That won't guarantee. Okay. It's not like linear. It's not like least mean squared. We know that the objective function is convex, right? It's not like SVM dual. It is a quadratic convex optimization problem, right? You always have some global minimum. But for neural network, the objective function is super complicated. If you just draw some landscape of the objective function of neural network, it typically will be something like that. Right? So you have many local minimum. Right? And actually, which local minimum you're gonna arrive not only depends on your learning algorithm, it also depends on your initialization, right? Maybe you initialize here, right? Then you just stuck here, right? And this might not be a good local minimum. And some other initialization strategy might ask you, okay, why not I start here, right? Then I get much better local minimum, right? It depends. That's why you can now say the neural network can give you some global training, give you some global minimum. Okay. Although we have given this general and useful stochastic gradient descent for training neural network, we have yet solved everything. Which have we left? Which part we haven't we discussed? Prediction. The prediction we haven't discussed, right? The forward pass, right? What's the key step in the stochastic gradient descent? Yes, exactly, right? We have the whole recipe, right? We know how to do that, right? But the key step will be, okay, you are able to compute the gradient, right? Given any randomly sampled training example, xi, yi, right? You should be able to compute the gradient of loss with respect to model parameters on this example, right? Otherwise, how do you perform the update, right? So that is actually the key step of the neural network training, right? So if the neural network is a differentiable function, we know that each neuron performs some linear transformation of the input neurons, right? And then you perform some activation function. So whether this neural network is differentiable or not, it really depends on the activation function, right? If the activation function is continuous as well, like sigmoid, like tanh, like Gaussian, like sine, right? Of course, you can calculate the exact gradient of the neural network, right? But what if the activation function is not differentiable? For example, the ReLU function, right? Obviously, it's not differentiable, right? Then what should we do? Yeah, we can use subgradient, right? It's like hinge loss, right? ReLU is like hinge loss, right? You can use subgradient, right? And so in general, I mean, in theory, we are able to compute the gradient, right? If it's not differentiable, we can calculate the subgradient, right? The major bottleneck comes from the cost, right? We know that for SVM or for least mean square regression, they in general can be viewed as just one level neural network and with a simple structure, right? But if the neural network is very large, is very deep, the computation will be a lot harder, right? And it's not uncommon that modern neural network contains 1 million parameters, like for right now, we know that large language models are very popular, right? Like ChatGPT. The whole ChatGPT contains like 70 billion parameters. Even cannot be stored in one commonly used memory card. Right? This is very, very large. Like, not to mention, like if I want to train that, I want to compute a gradient vector, which is 70 billion dimensional, right? So in that case, how do we efficiently compute the gradient? Right? It is okay, right? Because even for a single training example, you have to compute the gradient for maybe millions or even billions weights of the neural network, right? If you cannot efficiently calculate that, then forget about efficiency, right? You can even cannot finish one update. So that's why we need some efficient gradient calculation backpropagation. Right? So what is backpropagation? Right? Before that, right, let us first look at the checkpoint. Right? If you have a neural network, we can make prediction as for an input. Right? And then if I had a true label of the input, we can define a loss for that example. And then we calculate the derivative of loss with respect to each weight. Then we take the gradient step in stochastic gradient descent framework. This is the whole logic, right? So the key is that how we take the derivative of the loss with respect to every weight your giant neural network. Okay. So to introduce backpropagation, we need to review the chain rule. So what is the chain rule? It's just a rule to compute the gradient for a composite function. Okay. If z is a function of y is a function of x, then we know that z is a function of x as well, right? So if z is a function of y is a function of x, so we can view like z actually is a composite function of x, right? And how do we compute partial z over partial x? We can leverage the chain rule, right? The chain rule tells us that we can first compute partial z over partial y, then multiply it with partial y over partial x. Then we get our partial z over partial x. This can be represented by a dependency graph. Okay? So we use each node to represent a variable, like either it's function output or the function input, right? So we know z is a function of y, then we'll connect y and z. We make an edge starting from y pointing to z. And then we know y is function of x, then we initiate the edge from x to y. Right? And on each edge, we can associate with a partial derivative, right? It's just a partial of the target node or partial of the source node, right? So on this edge, this partial derivative is partial z or partial y. Right? On this edge is partial y over partial x. Right? And now, if we want to compute partial z over partial x, what can we do? From the graph structure, we just look at the path from x and z, right? So we have one path from x to z. Oops, I want to use another color. Right? And I just multiply the partial derivative along the partial derivatives along this path. Right? So I got two partial derivatives along this path. One is partial z over partial y, one is partial y over partial x. I just multiply them together. I get my partial z over partial x. Okay. That's the graph decoding of the chain rule. Any questions so far? Yeah, let us make it a little bit more complex. So now z is not only a function of one variable. Suppose z is a function of two variables, y1 and y2. Okay. And each of the y1 and y2 is also a function of x. We know that z definitely is a function of x, right? Then how do we compute partial z over partial x? Let's go back to the graph representation, right? We first write down the dependency graph. Z is a function of y1 and y2. So you see that two edges pointing to z, right? y1 to z and y2 to z. Associated with each edge will be the partial derivative, which is partial z over partial y1 here, right? And partial z over partial y2 here, right? And meanwhile, we know that y1 is a function of x. y2 is a function of x. That means x connects to y1, x connects to y2, right? And again, associated with each edge will be the partial derivative. Right? So it's partial y1 over partial x and partial y2 over partial x. Right? So now if we want to compute partial z over partial x, from the graph structure, right? From the graph view, we're gonna look at all the paths from x to z. Right? How many paths do we have? Two paths, right? One is through y1, right? One is through y2, right? Now our computation is to add the results across every path, right? For one path, the result just the multiplication of all the partial derivatives along that path, right? And then you just add up all those results together, you got your partial derivative. Right? So from path 1, right, which is starting from x, then y1, then z, the result will be just multiplication about the partial derivatives along this path, which we know is partial z times partial y1 times partial y1 over partial x, right? And if you look at the second path here, right? Again, you're going to multiply the partial derivatives along that path will be partial z over partial y2 times partial y2 over partial x, right? And you want to get the final result, partial z over partial x, you're going to just add up. You can just add up the result for every path, which is just here, right? And then you get partial z over partial x. So you can see that the chain rule can be very intuitively represented by the dependency graph, right? On your dependency graph, if you want to compute any node, any partial derivative over any node, right? You just enumerate every path from your source node to your target node, right? And maybe you many paths, right? And then you just multiply, for every path, you just multiply the partial derivative along that path, right? And you add up those results across the path. You get your final partial derivative result. Does this sound reasonable? Okay, and you will see later, the backpropagation essentially is to carry out this chain rule on the dependency graph represented by neural network. Okay, see you on next Tuesday.